Today we're going to talk about samples. When you do studies, samples are drawn, and then we're going to try and understand the nature of those samples. And we do that through distributions. When people run studies and we read studies, we're interested in the characteristic of each of the sample distributions. But when you have a patient in your chair, your question is more related to what distribution is your patient a member of. For example, when you look at IOP, you're trying to decide, is my patient a member of the non-glaucoma population, or is my patient a member of the glaucoma population? And that is based on some characteristics that we're going to talk about. Now, when we talk about samples, we tend to focus on means and differences between means. We need to consider the range of normal and the range of treatment values, because again, we're assigning people to distributions, so we want to know what is a reasonable range for a person that's normal, what is the reasonable range of a person who has a particular disease. The range of values tend to have different shaped frequency distributions. Now, a frequency distribution is basically you have an x-axis which labels things. For example, if we were talking about height, it would be from short to tall. And the frequency is how many people are at each level of height. And so there's kind of a peak height for the population, and then it trails off to very few really, really short people and very few really, really tall people. There's a different kindness. The first characteristic we talk about is skewness, and people can be symmetrical in their distribution, or they can pile up at one end and kind of trail off at the other in either a positive or negative way. If you think about glaucoma values, for example, the distribution tends to be there are a lot of hypotensive patients that trail off into this area, but there's also a lot of glaucoma patients who have very high pressure values. So the distribution tends to be a little flat. If you're talking about heights, it's pretty normal, a mesokurtic distribution. It's kind of got this bell-shaped. If you talk about the VA of emmetropes, it's a very peaked distribution. Emmetropes fall within a very narrow range of visual acuity. So they're maybe around, they're about, a little bit, 0.4 diopters, maybe hyperopic, but it falls pretty quickly on either side. Even the distribution of all people in terms of visual characteristics tends to be a little leptokurtic. There are a few people that are really hyperopic and a few people that are really myopic, but for the most part, people are around this range. You would expect, if you were looking at a distribution of myopes versus emmetropes, that there would be this little bump and you would see lots of myopes. We'll maybe see an example of this later, but for right now, I just take my word for it. It's maybe a little bit of an expansion, but definitely not bimodal, in which there are two bumps, one for myopes, one for emmetropes, and maybe a third for hyperopes. So the steepness of the curve is called kurtosis. So we have one way or the other for skewness. Steepness, or peakedness, I guess, is kurtosis. Okay, well, there are all types of distributions. When we talk about a sample, That's a specific sample of individual observations. This is the only thing we can measure directly. We take a sample, we look at its mean and standard deviation, various different characteristics, but we get our statistics from this. All the other distributions that I have labeled here are hypothetical. We don't know the population of anything unless we're doing some specific study and we want to know just that particular area, like the average score for a particular school. That would be the school, would be the population, and we would get it. But if in general we're looking at studies that talk about myopes, we want to generalize to the greater population. And the population is all individuals that can be sampled. And generally speaking, when we are looking at studies, we're not only looking at individuals as they are today, but as we kind of make the assumption we're talking about people in the future as well as the past. But this is hypothetical. We can't look at them all. We estimate the parameters of the population from the sample. Similarly, we have sample means. That's all the possibilities of sample means if you were to do the study an infinite number of times. You don't do the study an infinite number of times. You do it once, and you get one mean. But if you were to do it a bunch of times, what are all the possibilities? What's the distributional characteristic of the means from a study that you've done over and over and over again? Again, we don't directly calculate this. This is hypothetical. This is the science of statistics looking at this. Sample statistics, the possibility of sample statistics. Now that can be, that could be the mean like we have up there, the standard deviation. It could also be t-tests. So you're comparing two groups. There's a difference between the means. That has a distribution. You have, you calculate a t-statistic. That is a single value, but again, hypothetically, if you were to replicate this study over and over and over again, infinite number of times, you would get a distribution of the t-statistic. And we'll talk about that in a couple weeks. All right, so how do we describe distributions? Well, we talk in terms of the center and the spread. The center of the distribution is usually described by the mean, which is, you all know this from, probably elementary school. You sum the observations and divide by n, the number of values. The standard deviations is the average deviation from the mean. Now, it's a lot like a mean in the sense that you sum stuff up and then you divide by the number of items. It's a little bit different because we are using this sample to estimate the population. And because of that, we're dividing by n minus 1 rather than the number of observations, because the population standard deviation is going to be a little bit bigger than the estimate. And this estimate gets a lot bigger if your sample is small. So if you have 5 people, you're going to increase it by quite a bit because you'll be dividing by 4 instead of 5. But if you have 100 people, you're dividing by 99 instead of 100, and that difference isn't so impactful. Now, when we talk about sums, we're talking about the x minus mean squared. But let's just consider first an observation. Just like when we were adding up for the mean, we summed our observations, the values, whether it's IOP, acuity, whatever, or height, where this is an individual person's value. We subtract it from the mean of all the people in our sample. And if we were to just sum this, just sum the x minus the mean. Now, when we talk about x minus mean, we're saying we have let's say this is the mean height of a person. This person over here, remember, short to tall, is a little bit taller than the mean. So we take x minus the mean and we get a value. Over here, the person was here, we would take x minus the mean, we get a negative number, and we could sum all the positives and all the negatives, And if we did that, we always get 0. That's kind of the definition or the primary characteristic of the mean. The sum of the residuals on this side is equal to the sum of the residuals on this side. So it's always 0. Well, always getting 0 dividing by n minus 1 is always going to give us 0. So what we do is square this value. So we take the difference, we square it, we add them up, divided by n minus 1. Now we have squared it, so we have to go back to the original scale. So we take the square root. We've called this kind of the average deviation. Now we could just take the absolute values, sum all those up, divide by n, and get the average deviation. This particular value has some characteristics that fit well within the science of statistics, the theory of statistics, so that this works, whereas the absolute average deviation does not. All right. When our distribution is skewed, sometimes people will report the median and percentiles. So the mean is the sum, the median is the middle number. And you rank your numbers and it's the middle value. So if I had 3, 2, 1, 4, 5, the middle number of 3, 2, 1, 4, 5 is 1, but that's not really the middle. You have to rank the numbers into 1, 2, 3, 4, 5 and get the median. So the median would be 3 in that case. The mode is the most. In our little example of 1, 2, 3, 4, 5, our distribution is completely uniform, flat, and nothing is more frequent. But most distributions tend to have a point where you have the most values. Now, because it's a sample and because things bounce around a lot, the mode is very variable and not really used at all. We speak of bimodal distributions when we notice that there are 2 peaks in the system. A lot of times, the AMA has recommended, the American Medical Association has recommended that we use 15th and 85th percentiles. So 15% of the people down at this end, 15% of the people up at this end, 15% up here. This is 85% of the population. So 15th and 85th percentile. I'll be honest, I don't see that very much in optometry. Most of the time, people report the range. Now, the range is the largest number minus the smallest number. So they actually don't report that as much as they report the largest number and the smallest number. So if this was 0 and this was 100, they would report those two numbers. But a lot of times, because one of the things you want to understand the nature of this distribution, is it symmetrical? Is it non-symmetrical? What's the deal? So when you are given the mean and the standard deviation and the mean minus 2 standard deviations will give you some information. So if that number is less than 0, in other words, 2 standard deviations is over here, and that's a biologically implausible number, then you basically assume that the distribution is skewed to the right. Because you see the mean kind of pulls things over here. Well, if these numbers weigh heavily on that x minus, it could make for a big standard deviation, and it would be over here. If the numbers are biologically too extreme at the other end, then it is a negatively skewed. You've got numbers tailing off over on the left. So if the distribution is symmetrical, then these are some percentages that it's good for you to know. 68% of the cases fall within plus or minus 1 standard deviation. So 100% of the cases minus 68 is 32% are outside the center of of these two standard deviations. So +1 -1, those two equals 2 standard deviations. And so that's 32% of the people outside of this center 2 standard deviations. You divide 32 by 2 and you get 16% of the values of the population are above or below 1 standard deviation. 95% plus or minus 2 standard deviations, that's a 4 standard deviation width. 95% of the observations will fall within that. And 100 minus 95 is 5% of the population is outside the center. And 5 divided by 2 is 2.5%. So if you have 2 standard deviations, if your patient is 2 standard deviations above the mean, they're likely to be, and the distribution is symmetrical, they're likely to be 97.5% of the population is below your patient, 2.5 is above. At 99%, it's 3 standard deviations. Now you remember that curve was symmetrical and had these tails. So the numbers with 1, 2, and 3, they change quickly from 68 to 95%, but then to go from 2 to 3 standard deviations, you're just accounting for 4% more. As we mentioned before, not all distributions are symmetric, so these things don't necessarily apply to non-symmetrical distributions. All right, so we talked about the n-1. It's all because you're estimating the population from the sample, so it's a little bit bigger. One further note about this, if generally speaking, no matter what the shape of the distribution is, all observations fall within plus or minus 5 standard deviations. That's such a big difference, though, it's not really that useful a piece of information. But you won't find, if your patient is 5 standard deviations from the mean of the normal, you can be pretty sure they're not a member of a normal population. Now there's this handy little statistic called a Z-score, a standard score. And the Z equals x minus the mean divided by the standard deviation. So if we have a mean of 100, let's say this is the mean and it's a symmetrical distribution. The mean is 100. And actually it doesn't matter whether the distribution is symmetrical or not. A Z-score is a Z-score. And let's say we had a number 116, which would be up here someplace. So 116 minus 100 is 16, and the standard deviation in our case, we're calling it 16. So 16 divided by 16 is 1 standard deviation from the normal mean. So instead of reporting your results as 116, they could say it's 1 standard deviation above the mean. The same way if it was 84, it'd be 1 minus 1 standard deviation. If your patient had a score on this test of 132, 132 minus 100 is 32 divided by 16 is 2 standard deviations. So they'd be out here someplace. 2 standard deviations from the mean. And 2.5% of the population would be above that. It's pretty common to talk about people. You check to see if people are 2 standard deviations above the mean, and then you're saying they're not normal. They're not in this, whatever your population is. Could be glaucoma patients, but they're not part of this distribution because they're greater than 2 standard deviations above the mean, or they're 2 standard deviations below the mean. If x was 148, it would be 48 divided by 16, or 3 standard deviations. Only 0.5% of the people would be outside of that. Now, standard scores are very handy because sometimes you're going to read a paper and you don't really understand what a measurement is. I don't know if you've had logmar much, but if you had a logmar of 1, is that a good value or a bad value? You don't really know. But if they give you the mean of normal, which would be, say, 0 plus or minus 0.2, then you could take 1 minus 0 as 1 divided by 0.2 is 5 standard deviations, and you say, oh, 1's bad. So you can tell because of the standard score is consistent across all measures. So you could compare if a person's IOP is where their Z-score is for that, and other measures to get at where they are in terms of normal with respect to glaucoma. All right, let's look at an example. Here we have heights, and we're going to look at the frequency distribution of female heights, female optometry students. We see down here, let's see if we can get that down a little lower. Okay, so we see that our range is from 55 inches to 75 inches. Actually, in our little table over here, we only go from 59 to 72. I guess this is exactly the same. I think this is a frequency distribution that I simulated based on the means and standard deviations. This was the original data that simulation was based on. So we hang out a little bit more on the ends. That's that, for example, that's that concept where the population has a little bit more spread than the sample. We see that here when I simulated this for thousands of people. There's more on the outside. Our tails go further away, a little more spread. Over here we have the same sort of thing. We have a distribution, and this up a little. And we have, there was one woman with a height of 59 inches. So she was 4'11". Somebody else 6'2" at 60, and so forth, up to 72. Now, we found that the mean was 65. So the mean's right here. And the standard deviation was 2.74. So one standard deviation above the mean is 67.74. So it's in this neighborhood. So 68 would be, outside one standard deviation. All right. Now we look at males. It's interesting to look at the males. Their shortest person was 65 inches, and the tallest person was 78. Now, notice that the shortest male was the mean of the women. So men are generally taller than women, but not all men are taller than all women. And one of the things that we do when we're looking at statistics is to try and determine how much overlap is there. The more overlap in your measure, the less sensitive it is to determine the difference between your populations. And remember, the goal is to determine which distribution your patient falls in. So if height is a test of gender, the question is, does your patient fall in the female distribution or the male distribution? And in this study, we had a mean of 71 for the males and 65 for the women. And this point right here, this little criteria, 68.13 inches, if you fall to the right of that, you are labeled, or you have a higher probability of being male than female. If you fall to the left, you have less. But let's think about this in terms of how we do tests. Remember we said that oftentimes people say, well, are you normal? You're normal if you're less than 2 standard deviations away from the mean. So females, their 2 standard deviations is right about here. So all these, if you were a female and you had a height that's a little bit greater than this, then you would be rejected, as your test would say you're probably not female. And that's probably true because there's this whole big pile of people here that are males. So the probability of you being female isn't very high. But notice you're saying if you're greater than this number, your decision isn't going to be too bad if you say you're not female. But you would be really wrong if you tried to conclude, okay, you're not female, so you must be male. That is a strange thing about statistics. You can say, I'm pretty confident the person isn't female, but you cannot say, I'm pretty confident if you're in here, in this area, you can't be confident that you're female and not male, because there's a lot of people here that are male. In fact, at the exact cutoff, all the people that are to the right of this line are more male, tend to have a higher probability of being male than female. So understand that distinction. It's really important as you're going through your career here. You're going to hear, for example, if your IOP is greater than 22, then you're not normotensive. You don't have a normal IOP. But it does not mean that you're not glaucoma. You don't have glaucoma, because a lot of glaucoma patients have values less than 22. So you can rule out normal in this direction, but you can't claim the opposite is true. We're going to see that all over the place in our statistical practice. So in summary, the mean and standard deviation are used to summarize the center and spread most of the time, particularly if your observations are symmetrical. Median or percentiles or range are used to summarize the center and spread for non-symmetrical or skewed distributions. If you are not told the distribution in the literature, then you can judge whether it's symmetrical or skewed by determining if the mean plus or minus 2 standard deviations is a biologically reasonable number. And just because a test value falls within 2 standard deviations does not guarantee your patient does not have a disease.